Vision language models like CLIP, trained with contrastive learning on large scale noisy data, are becoming increasingly popular for zero shot recognition problems. In our work, we improve three aspects of the contrastive pre training pipeline. Firstly, our complexity action and text spotting CAT filtering removes many non-informative text-image pairs from a noisy billion-scale dataset while achieving improved performance. Secondly, we study the utilization of an external pre-training image model and propose a concept distillation approach that does not change training complexity while outperforming other approaches. Finally, we modify the info-NC loss and propose an importance sampling approach to upsample the importance of hard negatives without adding additional complexity. On an extensive zero-shot benchmark of 28 tasks, our method achieves improvements on 19 tasks compared to baseline. Let us first discuss CAT filtering in detail. We filter noisy line 2 billion web dataset based on the following three criteria. Firstly, complexity. We build a fast rule-based parser that extracts objects, attributes, and action relations from text, and we use resulting semantic graph. We retain the caption if at least one relation to an object is present in the graph. Similarly, we do action filtering, which means at least one action should be present in the graph. Finally, image caption pairs in web scale datasets often display part of the caption as text in the image. On visual inspection, we found up to 30% such samples in Lion dataset. Minimizing the objective in these cases can correspond to spotting text rather than high-level visual semantics we would like the model to align to. Hence, we do OCR and remove images where OCR text match caption partially. Here we show the effect of doing the CAT filtering on the Lion dataset. Note by introducing the complexity and the action filter as shown in row 4, we are able to reduce the dataset size by 3x compared to row 1 while improving the performance on the Cocoa and Flickr tasks. You can see a slight reduction of performance on the ImageNet task, which makes sense because it is object-centric. Finally, if we add all the three filters, including text spotting inside it, it leads to increased performance across all the tasks. Our second improvement is called concept distillation. Recognizing visual concepts in images that correspond to objects and attributes in corresponding captions is crucial for alignment. We therefore propose to distill these concepts from a pre-trained teacher model to our image encoder. We first parse image captions using a semantic parser that extracts objects and attributes from text. Since captions may not have complete list of objects and attributes present, we train linear classifiers on top of with swag model and then generate top case pseudo labels. It is important in this process to freeze the backbone of the teacher model to make sure we retain the advantages of using a stronger model for distillation. During multimodal training, we do concept distillation by using the cross entropy loss with these pseudo labels vectors as targets on top of our DIHT image encoder. Our model reaps the benefits of recently proposed and publicly available unimodal vision models more effectively than other distillation approaches. This is because training linear classifiers on a frozen teacher model is inexpensive. There is no training overhead required as the predicted concepts are pre-computed and can be easily stored. For example, for storing the top k concepts where k is equal to 10, we require only 32 GB of additional storage. After predictions are stored, we discard the teacher model and thus bypass the memory and compute limitations of simultaneously running both the teacher and student models together like in standard distillation approaches. Here, ED refers to the standard embedding distillation, which is 60% slower and takes 8% extra GPU memory while being less accurate than our approach called CD here. In addition, one can try to use the swag model itself as the image encoder and simply freeze the model. However, while these models do well on classification tasks, they do not do well on retrieval tasks as indicated by the Cocoa and Flickr performance. One can, in addition, try to fine-tune these image encoder models and not freeze them. In this case, we see there is a regression on the classification task. Moreover, in all these logged locking of model or fine tuning approaches, we are then constrained to a particular architecture which may not be desirable in future. Our third contribution is the introduction of a better contrastive loss. Contrastive learning has quickly become the de facto approach for multimodal alignment, where most prior works focus on multimodal info and C objective. While this approach has enjoyed immense success, when learning from large noisy datasets, uniform sampling can often provide negative samples that are not necessarily discriminative, hence requiring very large batch sizes. We leverage an importance sampling approach to reweight negative samples within a batch so that harder negatives are upsampled in proportion to their difficulty. Consider this example of 4 text and image pairs. In this case, we emphasize difficult negative pairs that have high matching score but are actually negatives, while ignore the easier negative pairs by downsampling their weights. Here we show results on 2 datasets, our cat filter Lion and PMD 63 million. Note that in both datasets, hard negatives lead to improvements. Gains are particularly significant for the PMD dataset since it has less noise and hence less hard negatives that are actually positives. Finally, we combine all the improvements and evaluate our models on a zero-shot benchmark of 28 tasks consisting of 18 image classification, 8 cross-modal retrieval, and 2 visual question answering tasks. On the Lion dataset, we improved performance on 19 out of 28 tasks. On PMD, we improved performance on 27 out of 28 tasks, and that too by a significant margin. We also compare our approach to state-of-the-art clip and open clip models for different architectures. Note that our approach significantly beats the state-of-the-art models for various tasks.